Good morning, everyone. Today I will be discussing privacy-enhancing technologies, or we call PETs, in the context of medical data privacy. With the growing digitalization of healthcare, ensuring data security while maintaining accessibility is a major challenge. This presentation will explore PETs, their benefits, challenges, and future directions in the medical field. PETs refer to a range of techniques that protect personal data at a technical level. They enhance digital security and privacy while allowing organizations to process and analyze data securely. PETs help organizations collect and use data without exposing sensitive personal details, making them crucial in the medical sector. Medical data comes in various formats, including electronic medical records, medical imaging, genomic data, and real-time physiological monitoring. Due to its sensitive nature, unauthorized access, data breach, and the inside threats are significant risks. Additionally, sharing medical data among institutions increases the risk of privacy violations, making security measures essential. Protecting health data privacy is crucial and complex in the medical field. To design an effective system, we first need to analyze its requirements, both functional and non-functional. Functional requirements focus on core capabilities. Medical data is scattered across hospitals, clinics, and research institutions, so the system must support secure cross-institutional data access. It should handle various formats. Strong security measures must be in place to prevent breaches. Additionally, anonymization or pseudonymizations should be supported to allow data sharing without exposing personal details. Non-functional requirements ensures the system performs reliability. It must be highly available, scalable, and capable for handling large data requests, especially as user numbers grow. Features like load balancing and horizontal scaling help maintain stability. Compliance with regulations like GDPR and HIPAA is also critical, requiring audit trails, data minimization, and user consent mechanism to protect privacy and ensure legal adherence. In summary, a well-designed medical data privacy system should enable secure cross-institution access, protect patients' data through encryption and anonymizations, be scalable and reliable, and comply with strict privacy laws. Meeting these requirements will support medical research and innovation while safeguarding patient privacy. PETs covers a wide range of different tools and technologies designed to protect personal privacy in an increasingly digital world. These tools and technologies allow individuals and institutions to control when and where personal information to disclose. The development of digitalization in the field of healthcare is widely adopted, and a large amount of patient health data is generated. The proper use of data is very important for the development of medical research institutions. However, there are many problems in the sharing process of medical information at present. Medical data is easy to be overwritten or lost in the process or transmission, and it is difficult to share with each other. The phenomenon of data island is very obvious. In addition, most of medical data is stored by the hospitals. Once the data is overwritten and used without specific knowledge, it will cause security risks like conflicts between doctors and patients. Health data sharing is of great significance in medical field. It can promote medical research, the accuracy of medical decisions, and the development of personalized medicine, promote new medical breakthroughs, and improve diagnosis and treatment outcomes. However, PET technology is not always a magic medicine for any cases. In some occasions, health data sharing faces a number of harsh challenges so far. Privacy and security of medical data is one of the most troublesome challenges. Sharing health data can trigger the disclosure and abuse of personal privacy, which will induce unexpected risks to patients and hospitals. Besides, medical data is scattered and stored in centralized databases at various medical institutions, resulting in pieces of data difficult to integrate effectively. This phenomenon not only limits the optimal utilization of medical research, clinical trials, and resources, but also seriously hinders the further development and innovations of the medical industry. Aiming at the problems that privacy of medical data shared between patients and medical research institutions is easy to leak, and the use of medical data by patients is uncontrollable. A medical data privacy protection scheme supporting controlled sharing is proposed. The first is data encryption and desensitization technology. Data encryption technology is one of the commonly used data privacy protection methods. Symmetric encryption or asymmetric encryption algorithm is used to encrypt health data to ensure the confidentiality of data during transmission and storage. In addition, desensitization technology is also a common means of data privacy protection by removing or replacing sensitive information in medical data, such as names, ID numbers, and so on, to reduce the sensitivity of data. The second way is access control and identity management. Technologies, access control, and identity management technologies are used to restrict access to health data and ensure that only authorized person can access and use the data. The access control mechanism includes identity authentication, authorization, and right management. The access to health data can be controlled based on their user's identity, role, and right level. The identity management technology is used to manage the user's identity information to ensure the authenticity and uniqueness of the identity. The third approach is data anonymization and camouflage technology. Data anonymization and camouflage technology aims to reduce the risk of re-identification of medical data, thereby protecting the privacy of data. Anonymization technologies protects the privacy of data subjects by removing or disturbing information related to personal identity, such as anonymous coding, generalization, and desensitization. Camouflage technology replaces real data with fake or noisy data to confuse sensitive information with privacy features. The last one is privacy protection algorithm and protocol. Privacy protection algorithm and protocols are specific technical means applied to medical data privacy protection, including differential privacy algorithm, homomorphic encryption algorithms, secure multi-party computing. These algorithms and protocols ensure the confidentiality and privacy of data by introducing privacy protection mechanisms in the process of data processing and sharing. In-house data privacy protection technologies. Various methods and technologies have their advantages and limitations. Data encryption and desensitization technology can effectively protect the confidentiality of data, but there are some limitations in data analysis and utilization. Access control and identity management technologies ensure legitimate access to data, but there are challenges to data sharing and collaborative research. Data anonymization and camouflage techniques can reduce the sensitivity of data and the risk of individual identification. But data may lose accuracy, and its integrity is also affected. Although complex algorithms provide a higher level of data privacy protection, the cost is sometimes unaffordable for hospitals. While PETs show great potential for protecting personal privacy and data security, they still face many challenges and risks in actual-world application. To overcome these challenges, healthcare organizations need to take a variety of measures. In medical field, many PET technology require a lot of computing resources. For example, hospitals may need to use homomorphic encryption to protect data privacy when processing large-scale medical data. However, this will cause a significant increase in computational expense. Due to the limited budget of medical institutions, many hospitals and research institutions may not be able to afford the high computational costs, so they prefer to use traditional, less costly methods of data processing. This limits the PET's adoption and spread in the medical field. In encrypted data processing tools, data cleaning and pre-processing is a major challenge. In medical data processing, data cleaning and pre-processing are key steps to ensure data quality. However, when using encrypted data process tools, such as a multi-party secure computing, the data cannot be cleaned and pre-processed directly in the encrypted state. If medical data is not sufficiently cleaned and pre-processed before encryption, it may lead to inaccurate data analysis results, affecting the reliability of medical diagnosis and research. Although PETs is supposed to protect data privacy at first, in some specific occasions, computing can still reveal sensitive information. For example, in a multi-party calculation, if the results of calculation are based on only a few data points, an attacker may infer the original data from these results. The privacy protection of medical data involves laws and regulations in several countries and regions. However, the legal framework for the use of PETs in cross-border data transfer is unclear, especially when privacy regulations differ in different countries. For example, the issue of privacy protection in cross-border data transfer, how to use PETs under the legal framework of different countries is still an unsolved problem. The complexity and technicality of PETs requires users to have certain technical knowledge and skills. If PETs are not used correctly by healthcare workers, data privacy protections may fail and even lead to data breaches. Moving forward, PATs will play an increasingly critical role in medical data privacy. Addressing computational and regulatory challenges is essential for broader adoption. Training programs must be implemented to educate healthcare professionals on using these technologies effectively. By leveraging PATs, we can ensure secure data sharing, drive medical research, and enhance patient care while safeguarding privacy. Thank you for your time. I hope this presentation provides valuable insights into PAT in medical data. So let's start with the motivation. Medical data is inherently sensitive. Think about diagnosis reports, lab results, genetic information. Yet collaborative access to such data is vital for research, insurance, and referrals. However, traditional sharing systems often fail to protect data integrity and privacy simultaneously. We see frequent data breaches and lack of control over who accesses what. Our goal is to design a system where patients remain in control and sharing is auditably, secure, and selective. So, what were our project goals? First, we wanted to build a secure and decentralized system for medical data sharing. Second, the data owner, typically the patient, should be able to grant and revoke access at any time. Third, the system must guarantee data confidentiality, even in the presence of untrusted third parties. And finally, we aim to demonstrate a working proof of concept, not just a theoretical design. Here is an overview of the architecture. It consists of several key components. A data owner who uploads encrypted medical data to IPFIs, a data requester such as a doctor or researcher, a proxy which transforms ciphertext but cannot decrypt them, and a blockchain layer which stores access policies and transaction logs. The data flow begins with the encryption and upload continues with access request and authorization, and finally enables data decryption, all without exposing plain text to intermediary. Now let's dive into two core technologies. First, blockchain provides a decentralized ladder to record who accessed which data and when. We use smart contracts to enforce access control policies in a transparent and tamper-proof manner. Second, proxy re-encryption enables one party to encrypt data and another to decrypt it, with a re-encryption process by an untrusted proxy. This allows the data owner to delegate decryption capability without revealing their privacy key. The sharing process works in 5 steps. The data owner encrypts the data with their public key. The encrypted data is uploaded to IPFS, and a hash is stored on-chain. When a data requester wants access, they submit a request via the smart contract. If approved, the data owner generates a re-encryption key and sends it to proxy. The proxy transforms the ciphertext so that the data requester can decrypt it, but without learning anything themselves. This ensures that only the intended recipient can access the data, even if they didn't originally encrypt it. A critical aspect is access control. Instead of relying on centralized access policies, we use smart contracts to store and enforce access rights. The contract logs every request and approvals, so there's an immutable record of data access. More importantly, the data owner can revoke access at any time by disabling the re-encryption key. This is what gives our system its unique combination of flexibility, transparency, and privacy. Security was a top priority. Here are some of the guarantees our system provides. Confidentiality, data is encrypted end-to-end. Integrity, the blockchain ensures logs are tamper-proof. Unlinkability, the proxy cannot link the original and re-encrypted data. Revocation, access can be revoked by the data owner. We also mitigate risks like replay attacks and unauthorized access using nonce values and access tokens. System initialization and key management. Design depends mostly on secure and effective generation, coupled with distribution and management of cryptographic keys in a decentralized setting. The system has to be based on strong, well-tested security mechanism if private key held by patients as well as institutions are to remain confidential. The design of the system has to include clear trust assumptions and strong fault tolerance policies, since any possible breach at the key generation center could cause widespread vulnerability. Scalability and blockchain performance. Scalability rapidly become a major concern since the system uses blockchain to store authorization parameters and preserve data integrity, especially with more participants and the participation of the miner nodes in producing re-encryption keys add extra computational load and could cause synchronization delays. Real-world deployment depends on addressing these performance bottlenecks. Integration and interoperability, including this system into existing medical infrastructure, especially hospital information system, presents many practical engineering challenges. Many legacy systems just weren't designed to handle current cryptographic operations or interact with blockchain technologies. So compatibility and interoperability are significant issues during deployment. Seamless interoperability across various platforms, while preserving security and compliance, has to be considered. Privacy and anonymity assurance. Maintaining user anonymity on the blockchain calls for deliverable design of address generation and data sharing system, preventing the anonymization by means of traffic analysis, metadata leakage, or correlation attacks increase further engineering complexity, particularly in relation to the design of the blockchain interface. User trust and usability design. For a system in engineer point of view, the plan has to be obvious for non-technical users, including patients and medical professionals. Understanding data flow in such cryptographic systems, setting access controls, and managing key could create usability issues. Adoption depends on confidence in the system's openness and efficiency. This system suggests a privacy-preserving plan for regulated sharing of medical data by means of blockchain and proxy re-encryption technology. Medical data is first encrypted using proxy re-encryption in this method before being sent to a proxy server. The proxy server reduces the storage and processing load on the blockchain and transforms the encrypted data to allow safe sharing. While patients decide access rights for their medical data and interact with the authorization management node to activate user authorization, distributed miner nodes on the blockchain work together to create proxy re-encryption keys, so ensuring controlled sharing of the data. At last, performance and security studies show that the suggested method allows dynamic sharing of medical data while protecting patient privacy. so improving the general availability of medical data by providing notable benefits in terms of functionality, communication overhead, and computational cost.